Hello students, welcome back to my YouTube channel. In this video, I am going to discuss about bar magnet as an equivalent of solenoid. What is bar magnet? Bar magnet is a magnet in the rectangular box shape like this, north and south pole. Okay, the pole strength of the north pole is, we can consider it as plus Q, Qm, and the pole strength of the south pole is minus 2. Okay, if the distance between the two poles is 2L, then the strength of the bar magnet or this magnet, okay, that we can express by a term that is magnetic dipole moment. Magnetic dipole moment, small letter m is equal to magnitude of one of the pole strength into the distance between them, that is Qm into 2L, and the direction of m is similar to the direction of the 2L. The 2L direction is from south to north. Okay, so the magnetic dipole moment of a bar magnet is in this direction, that is from south to north. This is a magnetic dipole moment direction of a bar magnet. Okay, so this term decides the strength of the bar magnet. What strength? This magnet field produced by this bar magnet. Okay, then next we will see what is solenoid. What is solenoid? Solenoid is a long wire wound in the form of a helix. Like this you can consider. Okay, like this. So you see this. The solenoid is similar to large number of circular turns are placed closer. These two are the neighboring turns. Okay. Then when the current flows through this solenoid, the current is circulating around it. Circulating current produces magnetic field and it is act like a magnetic dipole. Similar way, the current circulating through the solenoid produces magnetic field and the solenoid is act like a magnetic dipole. That means one end of the solenoid is act like a north pole and other is act like a south pole. The direction we can find out by right hand rule. Okay, here the current direction. What is the current direction? The current direction is in this direction. Okay, so we can apply the right hand. Curl the right hand in the direction of current. Then the thumb gives the magnetic field direction. So here this side is act like a north pole. This is act like a north pole, and this side is act like a, okay, and this side you can apply it and you can find it, this side is act like a south pole because you curl the right hand in the direction of current, then the thumb gives the magnetic field. So here the magnetic field is into, that means this side is act like a south pole. Okay, now you see this is the thing about it. Okay, then this solenoid produces magnetic field. The strength of the magnetic field is, we can find out by using a term that is magnetic dipole moment. The magnetic dipole moment of a solenoid, that is M is equal to NIE. What is N? N is the number of turns, I is the current, and A is the area of cross section, like this. This is the area of cross section and this is the magnetic dipole moment. What is the direction of the magnetic dipole moment? The magnetic dipole moment direction is the direction of the area vector. Okay, direction of the area vector, that can be found out by using right hand rule. Okay, then so the magnetic field due to the solenoid is similar to the magnetic field due to bar magnet. Okay, we can see what are the similarities between the bar magnet and the solenoid. Okay. The first one is the nature of the magnetic field due to a solenoid is similar to the nature of the magnetic field due to a bar magnet. Magnet. Okay. What is the nature of the magnetic field produced by a solenoid? We can find out that if a solenoid is like this, if this is a solenoid, through this the current is in this direction. Okay. This is the back side, the dotted one. Okay. Okay, so this way the current is to be flowing through this solenoid. When the current flows, one end of the solenoid is act like a north pole and other is act like a south pole. The direction of the magnetic field can be found out by right hand rule. Okay, how will you apply the right hand rule? Curl your finger, that means the right hand fingers curl in the direction of current, then the thumb gives the magnetic field direction. So here in this end, if I will apply, I am getting the magnetic field is coming out. That means this end is act like a north pole. This end is act like a north pole, and I am going to apply the right hand rule in this side. I am getting the magnetic field is entering into. That means this end is act like a south pole. Okay. Then what about the magnetic field? So here you see the magnetic field due to this is in this nature. Okay, originating from the north pole and like this. Inside it is from south to north, like this. Okay, this is the nature of the magnetic field due to a solenoid. Okay. The magnetic field due to a bar magnet is similar to that, north and south pole. Now we look at from the north pole, the magnetic field line is originate and come to the south pole, and inside the bar magnet, the field line is from south to north. The similar way here also. Outside the solenoid, the magnetic field line is from north to south, and inside the solenoid, the magnetic field line is from south to north. So from this, we can say that the nature of the magnetic field line due to a solenoid is similar to the nature of the magnetic field line due to a bar magnet. Okay, then the second one is cutting a bar magnet into half is like cutting a solenoid. What is the second? Cutting a bar magnet into half is similar to cutting the solenoid into halves. That means I have a bar magnet. Okay. One end is north pole, other end is south pole, and the length of the bar magnet is 2L. Okay. The magnetic dipole moment M is equal to Qm into 2L, where Qm is the pole strength of the north pole and the Qm of this is plus Qm and minus Qm is the pole strength. Okay. I am going to cut this bar magnet into two pieces. Okay. Into two equal halves. Okay. Now I am getting two other magnets. Two other magnets. Here is the north pole and south. Here it is the north pole and here is the south pole. Okay. Pole strength is similar. Qm, Qm. Here also Qm and Qm. This is plus, this is minus, because pole strength of the north pole is plus Qm. Okay. And the length is decreased. Here it is L and here it is L. Now you see, what about the magnetic moment of this? The magnetic moment of this is Qm into L, and magnetic moment of this is equal to Qm into L. So from this I can say that if a magnet, that is a bar magnet, is cut into two equal halves, produces two other magnets with the weaker magnetic properties. Here you see that here the magnetic moment is Qm into 2L, but here Qm into L. Okay. Then now we will see what about the solenoid. For a solenoid, this is a solenoid. Through this current is to be passes. So this solenoid is act like a bar magnet, or it will produces magnetic field. Okay. Then I am going to cut this. The total number of turns I am taking as N. Okay. Now I am going to cut this solenoid into two other. So I am getting two equal halves. Okay. Then what about the magnetic moment of this bigger solenoid, that is M is equal to NIA. N is the total number of turns. Now you see, what about the magnetic moment of this one, that is N by 2 into IA. Why it is N by 2? Because when it is cutted, number of turns are reduced by half. So here also M is equal to N by 2 into IA. So now we can say that if a solenoid is cut into two equal halves, we will get two other solenoid of weaker magnetic properties. Okay. So this is similar to the bar magnet cutting. Okay. Then this is the second similarities between the bar magnet and the solenoid. Then third one. The third one is the magnetic field along the axial line of a solenoid is similar to the magnetic field along the axial line of a bar magnet. Bar magnet. So I am considered a solenoid, and I am going to find out what is the magnetic field along the axial line of a solenoid. Okay. This is a current carrying solenoid. The length of the solenoid is 2L. The length of the solenoid is 2L. I am going to split this, that is, this is the line which is splitting the solenoid into two equal halves. That is, this O is the center of the solenoid. Okay. Then this is the axial line. Okay, line passing through the axis of the solenoid, and consider a point P which is r distance from the solenoid, which is r distance from the solenoid center. Okay, the radius of the solenoid is A. Okay, and I want to find out what is the magnetic field at this point P due to this solenoid. Okay, so the solenoid is similar to large number of circular turns are placed closer each other. Okay, a circular turn, that is, if a current is like this in a circular turn, a point P is along the axis of a circle which is at an x distance, and the radius is r for a circular turn. The magnetic field at the P point is B is equal to mu 0 Ni by 2 r square divided by r square plus x square all power 3 by 2. This is the magnetic field axis of a 110. If it is n10, n number. Okay, so the same principle we can apply here, and we can find out the magnetic field at the P point, because the solenoid is similar to large number of circular turns are placed closer to each other. Okay, then so to apply this, I am going to consider a consideration, that is, I am going to consider a small portion. The thickness of this portion is dx. Okay, thickness of this portion is dx, and this dx portion is x distance from the center of the solenoid. Okay, first of all, I am going to find out the magnetic field produced by this dx portion in the P point. Then I will integrate it. Then I will get the total magnetic field at the P point. Okay, so if small letter n is the number of turns per unit length, what about the total number of turns in dx? Okay, so that I am going to write here. In dx length is dn, that is equal how much? Number of turns per unit length is small letter n into dx. Okay, so we will substitute it here in this. So magnetic field at the point P due to this dx portion is dB, that is equal to mu 0 I by 2. What about n? N value is this much, that is n dx, divided by, here r is the radius, so we are using r square, but here the radius is a, so a square, divided by, okay, r square we can take, because here it is a radius is r, so they taken r is, here the radius is a, so we can take it as a square plus x square. X is the distance from the center to the point P. So here, if we will consider, we have to get the distance from this to this point. Here to this point is r distance. So this to this point is r minus x the whole square. Sorry, r minus x. Wait. So this is r minus x the whole square, all power 3 by 2. All power 3 by 2. This is the magnetic field at the point P due to this dx portion. Okay. Then the total magnetic field at the P point is the integration of dV. Here you see this. What is a variable here? Dx is a variable. That means the dx may vary from here to here. So if I am consider the center of the solenoid is at the origin. So from this all I will get it as this point is how much distance, that is minus L I am getting, and what about this point? This point I am getting the plus L. So this dx may vary from minus L to plus L. So here we can take the limit is minus L to plus L. Okay. Now we can apply the integration, that is b is equal to integration of mu 0 I into n dx divided by 2 into a square divided by a square plus r minus x the whole square all power 3 by 2. Okay, then now I am taking a consideration, that is if r is very greater than L, L is the length of the solenoid, that is a half length. Okay, if r is very greater than L, here you see that what about r minus x? R minus x is approximately equal to r, because here the integration is with respect to x and the limit is from minus L to L. Okay, so the limit if you apply it, you will get this r you will get. Okay, then next, and r is very greater than a, then what you will get this, that is a square plus r square r minus x the whole square is equal to what you will get, that is you will get r square you will get, because r is very greater than a. Okay, then what about the denominator term, that is a square plus r minus x whole square all power 3 by 2 is equal to r square all power 3 by 2. That we will get it as this 2 and this 2 cancel, so r cube we will get. So what about b now? B is equal to the constant, we can take it outside, that is mu 0 into small letter n I by 2, we can take it outside, and the a square also constant, that is also we can take it outside. Okay, then only the integration is here r cube we will get, that is also we can take it outside. The only the integration term is dx, so minus L to L. Okay, so apply the integration of dx. What about the integration of dx? Integration of dx is x we will get. Okay, so b is equal to mu 0 n I a square divided by r cube into x, the lower limit is L minus L and the upper limit is L. So apply the lower limit and upper limit, you will get it as mu 0 n I a square into 2L divided by r cube. Okay, here what about n into 2L? N is the number of turns per unit length and 2L is the total length. Okay, so this is the capital letter N we will get. Okay, so mu 0 into n I a square divided by r cube. Okay, then sorry we missed it here 2, here also 1 2 is there. Okay, so here this 2. Okay, then this is also 2 here, so I am going to multiply 2 pi here and 2 pi here. Okay, now what you will get? So now b is equal to mu 0 n into 2 into I into pi a square divided by 4 pi, this 2 pi into 4 pi r cube we will get. Okay, what about pi a square? Pi a square is this. This is the area cross section. So pi a square is the a. So what about n I a? Okay, n I a is the magnetic moment. So now b we will get it as mu 0 into 2m divided by 4 pi divided by r cube. This is the magnetic field at a point along the axial line of a solenoid. Okay, we will check it. This is the similar formula we will get for the bar magnet or not. Okay, so I am going to consider a bar magnet. Okay, sorry. This is a bar magnet, this is the north pole and this is the south pole, and this is the center. Okay, the length of the bar magnet is 2L. Okay, then P is a point along the axial line of a bar magnet, and that is R distant from the center O. Okay, the pole strength is here Qm, that is a plus Qm, and here it is minus Qm. Okay, the magnetic dipole moment is 2L into Qm. Okay, then the magnetic field at the point P is B equal to mu 0 divided by 4 pi 2m divided by R2. Okay, I am not going to the derivation. Okay, this is the magnetic field at a point along the axial line of a bar magnet. You see these two formulas. These two formulas are similar. That means magnetic field at a point along the axial line of a solenoid is similar to the magnetic field at a point along the axial line of a bar magnet. Okay, then from these two formula only these two are the thing is to be different. So, but if this B should be equal to this B, the M and this M should be equal. That means the magnetic moment of the bar magnet is equal to magnetic moment of the solenoid also. Okay, so from all these conclusions we can consider the bar magnet as an equivalent of solenoid.
Thank you for watching the video. Please subscribe my channel. If you like this video, please put like.